Theorem. She's probably in Katie type. I don't even want to watch. I don't know. I think she will. Alright, God's word. 2 Corinthians 12:9. My grace is sufficient for you. My power is made perfect in weakness. My question for you to ponder is, where do you feel weak right now? I know you need a response. You say it's not your thing, but it could be physical, it could be mental, it could be spiritual, it could be different things going on in your life, just like there are to me. My power is made perfect in your weakness. That's kind of like the stepping back and seeing the full artist picture of your life, or stepping back and being able to see that's why I had that trouble, so that I could be able to handle whatever it is that needs to come up later on in my life. For today, we need to do quite a number of pieces of things. My plan is still the same, that the Wednesday that you return will be a test day, and the Monday will be wrapping up whatever the rest of the things are going to be for the test and reviewing. You did get an answer or an assignment sheet that has just chapter 7 or section 7.1 on it. We're only doing that plus number 1 and number 2 on 7.2. So basically adding an idea called tau and sigma in the context of divisors. We'll talk about it either near the end of today, or if you have a gazillion questions to go through today, then it'll be at the start of the class on Monday, but it will be on the test. I do think it's something that's interrelated to what we're doing and fairly important. The last chapter is chapter 8 on cryptology. That's where we're going to end things, and what you have to decide with me by the end of that last week is whether or not you want fully or partially cumulative based off of the big picture. I didn't say no cumulative. I said fully or partially. Basically, do you want chapter 8 to count more or less in the final? I'd rather let you decide that based off of good or bad thinking on my part, or your learning, or whatever it might be. Because it does have the ability, once again, to cover up or replace your worst text. So, Alright, 6.3, we did not do Euler's theorem unless you watched the video or read stuff yourself, so there are some things that are new and there are some things that are very new within there. But I guess I would like you to take either 1, 5, or 15, and I want you to talk about how you get to the answer of any of those 3 with somebody nearby you. There's more than one route to the correct answer, and I don't necessarily think you have to have a real deep knowledge of Euler's theorem or anything like that to be able to do it. Once again, 1, 5, or 15, I'll give you about 45 seconds. I'm more interested in how do you get to that. Because there's no, the pattern repeats for 1,000 like it would repeat for 10. There's no, you don't need a bigger mod when 10 would do the same thing. Well, in this case, because you're raising it to a power, you're only looking at the last digit, so you don't really need the tens and the hundreds or the thousands digit. You just need the ones digit. So, for example, like 7 squared is 49, you really only need the 9. So I'll go back. I didn't do the problems the same way that your answer key did, and I'm just kind of picking off of what I think I just heard here say. I think number 5 and 15 are very similar. And once again, I don't think you have to have one route to get there. Let's talk about one of them. Carl, 5 and 15, which one is tougher? Okay, so if you look at number 15, it's basically saying take 7 and raise it to the thousandth place, and it says look at the units digit. Number 5 is basically the same problem, just using the third power. So it doesn't really matter. Okay, as I did this problem, I didn't do anything with, think of this like it could be mod 1,000 and then take 1,000 and make it into 10. I just did something like this, like 7 times 7 is 49, times this is 63, times this is 21. And the pattern just keeps repeating itself over and over again, like 7, 7, 9, 3, 1, 7, 9, 3, 1, 7, 9, 3, 1, 7, 9, 3, 1. So for example, 7 to the 5th acts like 7 to the 1st, 7 to the 9th acts like 7 to the 1st. So I just think of it like, to me it made sense that it's kind of like it's mod 4. And whether or not I even write this or not, if I can understand that, okay, this is like the 1st, 2nd, 3rd, 4th, or if you need something like 0, if it doesn't really matter, I can just look and say, okay, 1,000 is like 0 or 4, so the answer must be 1. Lizzie, you give me to look like I just talked to me a weird language. You multiply the... Correct. Well, so for example, I mean, the 10th digit doesn't matter. So if you're in 49, I take the 9, 63, 21, 7. I mean, like, it's going to repeat. So for me, the same idea with this, let 3 make 3, then 9, then 7, then 1, and then back around, and it's the same problem. So I just take the pattern and keep going for a while. So like, I know this is 4, take it out like 5, 6, 7, 8, 9, 10, 11, 12. Like it's always going to hit the 1 on the 0 mod 3, 0 mod 4, excuse me. If it's confusing to you, I would just write out more. Like if you don't see the pattern. So I would just focus on like, because 1,000 has a remainder of 0 when divided by 4. 999 has a remainder of 3 or mod 3. This 3 mod 4 is okay. I do like number 1, even though we didn't do that, just because I think it hits on some fundamental things, and we'll do a little bit of Euler's theorem. I'm most interested in what in the world is the vocab of the problem saying. I think if you understand what the vocab is saying, the problem itself, number 1, really isn't that difficult. The words say, find a reduced residue system. And they give you a bunch of integers, whatever they might be. So I think this is worth talking about. So what does that kind of sound like, but what does it really mean in this context, and then how do you approach it? And maybe the toughest question is just how do you not get it confused with something else that you already kind of heard before? so I think there's two things that are important about this. One might just be you want to see the answer, whatever it might be. So it's best you can explain what this means, Emily. Reduced residue basically means something like okay. So the reduced residue would be whatever those four numbers are. So in this case, 1, 3, 7, and 9. Okay. So let's go a little bit farther. Why is it called reduce? Or why is it called residue? And why don't the other numbers get invited to the party? Go ahead. Sure. Sure. So there's variations of these numbers that are larger. So if this was mod 10, there's 11 would also be the same as 1 and that kind of stuff. Go ahead. Yeah, and I think that's a good thing to kind of keep in your mind. Like, it fits what Emily said before. All the numbers are relatively prime. And I look at it as all the other numbers can make 0. And you might say, well, you're just double dipping and saying the exact same thing. It's all relatively prime, and that's true. But I kind of see it all as the same. Like, I can't make a 0 in mod 10 with a 3. It's just 3s, or even 3s and other numbers that are in this system. It's kind of like the numbers that are outside or inside the party, whatever you want to call it. Like, only create numbers that are their time. Just kind of the way that my mind sees it. If that's confusing to you, make it work. But reduced residue, one word difference, slightly different variation. Let's move forward. Euler's theorem. This is what you got a screenshot and a little video that I didn't even check to see how many looked or didn't look at it. This should definitely be in your notes at some point if it isn't already. And there's basically two stipulations. One is you have to have two numbers that are relatively prime. And then the second part of it is you can use the phi to be a little more efficient with your power. And actually, like, you become like 3 plus 5, 3 plus 4. My question for you is, what does this actually accomplish? What do you have to know? Does this make you more efficient or less efficient? Maybe if you looked at other problems, does this add anything other than just another theorem for you to kind of keep in mind? And I don't really care which way you go with the direction, but I actually want you to kind of have a discussion about, so what does this do for you? Big group. If you want to talk in the context of have a problem in front of you, go for it. That's up to you. Keep going. In the context of math, I've always heard it P. Yeah. In the context of this part of number 2. No. I don't think so. Tomatoes, big, bag, egg. It's all the same to me. Alright, so now I want you to go this direction. Here's what you got screencasted. I'm not going to go into a lot of detail about it, but the idea behind it is there are a lot of relatively prime ways to get towards your answer. So So for example, I said take a peek at 619, 620, and 621, and I'm not going to spend a ton of time there if we haven't been there already. 619 gets into like, so what do these numbers do and how do they stay in their own area? 620 has a decent example of how you could take the phi and be able to do a couple extra things with it. And then lastly, 621 gets into like how can you use an inverse or the idea to solve a system of whatever it is that you're looking for. So I kind of look at it this way. If 3 to the 4th is 1 mod 8, and that's the idea. Like if I can take the phi of this number and they're relatively prime, I'll always get a 1. My question for you to try to put all the pieces together is what's 3 to the 8? Small enough that you can do it behind 8. Okay, so let's play the game one more time. We select the phi of, let's go with 9. So phi parentheses, the phi of 9 is, I'll give you a shortcut how to get there in approximately 6 minutes or less, but 6. Okay. So I'd like you to come up with 5 to the something is congruent to something mod 9, and 5 to the something is congruent to something else mod 9, and try to keep these the same. Build something off of what you did, stay in your area, don't have to spin around too far, but take the concept of what's here. And then if you want to go a step farther with it, it'd be awesome if you could understand, like, oh, I kind of get where those numbers are coming from. I'd like you to take Euler's theorem, Fermat's little theorem, or any combination of the above. And the point of the start of this isn't that you couldn't have watched the video. It's more, I think it gets confusing and piling new things on top of old things when you're not quite ready. I didn't even want to give you the number to begin with because I wanted to see where you're at with it, but give me one that you're pretty sure of. Okay, 5 to the... Maybe somebody verified it. Just double check, like 5 to 6 is 1. Okay, 5 to the... Aaron? Another one? I don't disagree, that's... 0? I don't know. Okay, true. Which makes sense. I'm curious about the 3rd and the 9th. What? This is 8. So, 1. And 5 to the 9th is also 8. So there's some connection between all of the above. So like raising it to the third always makes -1, and if you square it, you get 1, and that sometimes you get back to that, whatever it might be. Like, there's other ways to break down powers. This will be a very clean way to get 1. So if I'm going back to, like, what does this do good for, is if you were trying to take some number raised to a massive power, it's a fairly efficient way to take a large number and get there. I'm not disagreeing with some of you that might say, in our number system, if this is mod 10, I probably don't need things like that because I might be able to know the pattern without any sort of formula over the top or under it or whatever it might be. And that's still true. But this idea of taking the phi and making a 1 is going to be important. Don't assume you always are going to get 1 in all these cases. And then this is one example that you saw that I just did that put this together. What I'd like you to talk about, and I only want about 20 seconds, is if this is the original problem, and this is on your semester exam, and I could solve it 3 ways, you should be okay with it. I think at this point you have at least 4 ways hypothetically heard and probably done. So 1 way is up on the board, talk about it, and then we're going to move into something that's new. But I'll go back. What I want you to be comfortable with is, what are some ways to solve this? He wants to talk through what in the world's going on here as well. So you should have many routes to get towards your answer. So you need to tie this together before we move forward. Well, I could give the bad answer and just say it's just the way it works with 5. But in all cases, it has to do with, because these numbers are relatively close to each other, taking a number and raising it to that exact same power is going to have some characteristics. So, for example, mod 9. This will always work with this. But what I'm saying is you can break this down and figure out where the 1 after came from. So in this case, cutting it in half means that 5 to the 3rd has to either be plus or it has to be negative. Because there's no other way to square and get 1 in this mod, because I can square something and still say 1 or multiply it by itself. What I wanted you to see is that if this is the case, there's got to be some route that makes that 1. So I like thinking it this way for the better use, but because this is 1, there's got to be some other way I can take a smaller portion of whatever it is and break it down. That's really all I was looking at. Like, so it has to be -1 because you don't. Okay, so I'm looking at least 4 routes. I'll start. One route is add 14s to 3s a bunch. It still might be the best route. Give me another route. Hear it. Okay, which means what? 14y equals 3. Okay, cool. Another route. Aaron. Absolutely, it's probably built into the first thing. But, I mean, you're only guessing up to 13. Yeah, that's lamb and dart at 4 will eventually hit something. Okay. You have 2 other routes. With powers, one has to do with the phi of the mod, if these are relatively prime. That's why this will work with 5 to the 6. Which seems like, oh, that's going to be pretty awesome because it knocks out the 5. It's okay, but as you get to the other part of the problem, I don't know if it really makes it that much simpler. So for example, I can make it so that this coefficient drops out, and I can make other pieces drop out, but eventually, usually, I'm left with a fairly large number of power that I have to still break down. There's another one where I could take and raise this to a higher power. So if you remember things like Wilson's theorem, there's more that would be there, but because if you're in mod 14, 15 makes 1, and the 1 drops out. Let's move a couple places that are new. So what I really like for today is I want to show you very, very efficient ways to use the phi function. If we have time to get to tau and sigma, awesome. If we don't, I just like that in math there are lots of interrelated things that don't just happen to work, but they help to explain a couple different things. So phi of 36 is 12. The page 609, I believe, is a chart that's in the back of your book. My question is, how can you use other values to get to 12? And we kind of got at that already, like looking at what you know or looking at the chart. Since phi is multiplicative, we just haven't really explained why. The phi of what times the phi of what work out just nicely so that you get 12 for the phi of 36. And once again, if you don't want to just go from what you have memorized, have the table ready. We're going to plow through a couple different things in just a sec. And I purposely do have the answer underneath. I can break 36 down in a bunch of ways, but the way that I break down has to be specific to this, and if that's the case, I'm in good shape. So in this case, Abe, I could pick 4 and 9, and I can be very, very confident that it's going to work. So in this case, the phi of 4 is what, 2, and the phi of 9 is 6. And I'm in good shape. 2 times 6 is 12. If this is the case that the numbers that you pick have to be relatively prime, it means I can't use what and what, Dylan, and use the multiplicative property. Well, 4 and 9 is going to work, but give me some numbers I want. 6 and 6, let's try it. So the phi of 6 is 2, I think, right? So 2 times 2 is obviously not 12. It has to do with they're not relatively prime in not all cases. Same thing with 2 and 18 and other stuff like that. Let's go here. The phi of 72 is 24. How do you get there? Don't disagree that the answer is right in front of you, but what's going to work? Good. 8 and 9. The phi of 8 is 4. The phi of 9 is 6. Okay, I want to do one more, and then I want you to really try to construct some answers. So if I'm doing the phi of 80, 8 times 10 isn't going to work, but if I pick something that they're relatively prime with each other, the phi of what times the phi of what is going to work. 5 and 16. Okay, so here's what I want you to try to figure out. with at least one person nearby you. How come, like, for 8 you keep getting 4, 16 you got 8, and then for 9 you got 6, and for 5 you got 4? Like, you've already kind of tasted a little bit of, like, how the fees work. What I'm really getting at is, okay, now I think you're believing that I can do this to get answers. My question is, how can you get from 9 to 6 fairly quickly, from 8 to 4, from 5 to 4, come up with some conjectures? And I want to see how close you can get to the, like, textbook formula in just a sec. Okay, so let's start with the easy one. Why is the fee of 5 4? Good. Prime number, always one less. The fee of 32 is 16. The fee of 8 is 4. The fee of 16 is 8. The fee of 128 is 64. Thinking behind that is, or I'll go with multiple of 2, but you're not wrong. Okay, so my question is, what about numbers like 9? Or you have the chart. I would think 9 acts like 2, which acts like 27. Conjecture. And you look like you have the answer. 9x, I would say 9x like 3. 27x like 9, which acts like 3. 81x like 27. I'm just picking numbers that are only built up of powers of 3. Let's see where you can go. Go ahead. So a third of the numbers are taken out. Cool. I would say 5 acts like 25. If Gabe is right, which I'm sure he is, otherwise I wouldn't have walked over by him and nodded. 5 is like 25, so the answer for 25 is what, 20? But for powers of 2, it does. Correct, powers of 2. Okay, so 25 I can be guaranteed it's going to be 20, and using Gabe's logic, the reason it's 20 is I take out 1/5 of the answers. So a fifth of the answers are all multiples of 5. Everything else is relatively prime. Now it gets a little bit more complicated. Like if I wanted to pick a number like 40, I can't just say take out half because it's even. I can't just say take out a fifth because it's a multiple of 5. I need the combo of all of the above. So instead of just saying taking exactly what he has, underneath that is the actual. Thank you, Captain Obvious. All right, let's go plan B. Where I'd like you to be is the formula for this section that I think is very, very important is actually Theorem 7.5, page 242. Page 242 has 2/3 of the way down the page has exactly what Gabe just talked about. I think it's noteworthy. is something like this. So if I could take any big number and break it down to its prime factorization, I don't really care how many, what power it's raised to. I just take that fractional portion of the answer out. So if it's divisible by 2, I take out half of them right away. If it's divisible by 3, I take out a third of the numbers because it's going to hit, it's kind of like the sieve of Aristophanes. Like that's going to cross off different numbers that are or are not going to work with it. Let's cruise. Phi of 25 is, don't look down. Okay, 20, right? So the idea behind it is I can take and get rid of a fifth of the answers and it will work. Because it's made up of 5 squared, and because of that I'm going to have what I'm looking for. How about the phi of 50? Don't look down. How much of it do you take out? And then how much more do you take out? I'll put it a different way. One way to do it is and you get 20 because right off the bat you take out, or you can do it the reverse, take out half the answers and then 25 is just like before, get rid of a fifth of the answers from that and you're going to have the exact same answer that 50 is 20. Alright. 10 factorial. I'm not interested in the big number if you want to feel verified that like yes, I do have the answer here. If you want to see it, see it. I'm more interested in what are the prime numbers. So definitely the prime numbers that go up to 10 are things like, there's definitely a 3, there's a 5, there's a 2 and a 7. Those are the prime numbers going up to it. Everything else double dip. So the fact that 8 is built into it doesn't really affect anything other than the fact that you don't need the full 10 factorial. You need a portion of that in a way that you can break it down and get the answer, which once again is what? 829,440. I just put this up here as I think it's review. If M and N are relatively prime, and because this is multiplicative, I can take the phi of 12 and use 3 times 4, but I can't take the phi of 16 and use 2 times 8. I only want about 8 seconds. Talk one more time. Why one and not the other? I think at this point it should be pretty solidified in your head. So, 8 seconds. Okay, so now I'm going to get at, I think we have the answer. I think if anybody sees something that's wrong. Indirectly, the reason you're doing this in number theory is it helps you understand how numbers are made in a different way than you've ever used before. So when you see 16, you see things a little bit differently after you study phi. You might not say it completely changes the way you think about it. This is the formula, just given one other way, taking prime numbers. Let n be a positive integer greater than 2. Every phi is even. Look at your chart if you don't believe me. If you believe the chart. So give me a little logic. I can't give an odd phi, or I only get even phi there and because. I look at it as like, so you have a lot of odd prime numbers that have an even phi. You have a bunch of even numbers that you take out half or whatever it might be, they stay even. a bunch of composite numbers that you take out fractional portions that kick it from odd to even. Numbers like 25 become 20. Numbers like 55 become 44 and other stuff like that. And so there's more to it. But taking out that fractional portion like a fifth or a seventh or an 11th or whatever it might be will always make it so that it goes from some odd multiple to some even multiple. Because of how the numbers are made up. For me, that's kind of a cool idea. All right, where we're going to end today is probably enough to give you a taste of what you can do in 7.1 and possibly the last two problems. For some of you that are saying, like, I want nothing when I get back from Thanksgiving break, get stuff done before you leave. If you're saying I want to do nothing and I'll do everything later on, you can pick what you want to be. Here are the two new notations, tau and sigma. If you want just what in the world are they both have to do with how many divisors are there, or what do they add up to as I get to a certain number. So for example, I think you also have the chart right next to the other things that you were looking at, 609, like you have these there as well. I'm going to kind of do two things at once and then just stick with sigma. So once again, sigma is the sum of all of the positive divisors. It's kind of like you're taking you're taking the other numbers, that you didn't just from a slide it to ago. So for example, the sigma of 5 is 6. Because I'm really focusing on 1 and 5 are the divisors of that. If I took the tau of 5, it's how many divisors I have. So in this case, there's two numbers that go into 5. They add up to 6. There are two of them. I'd actually kind of like you to do both at the same time if you can. Just build a little bit of a chart for your notes. So what's the sigma of 6 and then what's the tau of 6? What's the sigma of 7? What's the tau of 7? The purpose of that is I want you to at the very least start seeing a few connections with it. Be careful because a number like 4 is not a divisor of 6, even though they're not relatively prime. So I'd do something like the tau of 6 is 1, 2, 3, 6. You add up 1, 2, 3, 6, I got 12, right? The tau of 7 is 2, the sigma is 8. We saw something like this before. Anytime the number is prime, the only two numbers that go into it are 1 and that number. Makes sense that the sigma would be 1 bigger. What 8? 1, 2, 4, 15 and 4. Do one more. The tau of 9 is what, 1, 3, 9. Those numbers add up to 13. Okay. This is be a tougher leap, but can you conjecture, and you have a big table in front of you if you want. Can you conjecture, like, I think I can get to this by doing this. I think I can get to this by doing that. Maybe it would take something like looking at 12 or something like that. If you can't intuitively come up with a formula, it's not the end of the world. assuming I might get nothing unless you were looking at it on something with it like patterns you notice, things you might think are true, seem just like random numbers creating other random numbers. I think you can see primes fairly easily. I'll go back to, like, for me, I'm intrigued by something like 4 numbers go into 8. So does that mean 8 numbers go into 16, or does it just mean 5 numbers go into 16? The tau of 16 is 5. My hint for you has to do with, if you think of, and this might be beyond what you were going to guess, but if you can break down numbers into prime factorization, the power is what matters. So for example, 5 is 5 to the first. 6 is 2 to the first and 3 to the first. 7 to the first, 2 to the third. I'm just going to highlight what I want you to think about. 3 to the second, 11 to the first, 2 to the second, 3 to the first, 13 to the first. My question is, just with the taus, how do you get 2, and how do you get 4, and how do you get 4? Maybe this is the first one that actually does something with, like, the power to the second and the power to the first gave me 6. Okay. For 12. 2 to the second. 2 to the second, 4, 3 to the first. Let's just pick some other number, like the tau of 100. Your chart was that big, right? Is what? 2 to the second, 5 to the second? So the tau is what? Chart says the tau is 9. Doing the tau of 60. Go fast a bit. The same as 2 to the second, 3 to the first, 5 to the first. Can't be 12. What am I doing with the power? Kind of. I could say no. All I do is I take the powers one bigger and multiply. So all I did here is 3 times 2 times 2, 3 times 3, 3 times 2, 3. Just take all the powers, raise them one larger, and multiply. Alright, so it'll be later on the slide. I know that my time here says that I'm out of it, but just taking the powers, raising them one higher. We'll come back to more things with sigma and more things with tau on the Monday after Thanksgiving. My encouragement for you is you decide what you have to get done before break or after break with the time that you have, because 7:30 the Monday you get back is going to approach you very, very quickly. The test will be the Wednesday after Thanksgiving break. We'll wrap up a couple things with tau and sigma. They will not be the toughest thing for you to keep straight on your test, but we'll make sure we build in some review time on Monday as well. And hypothetically on Monday there should be a student wobbling into the back of the room too.